let me let me begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless this time we have together this morning, Lord. In your name I pray. Amen. All right, so let me get straight into the Fourier series again. And for the sake of me not forgetting a convention, just talk about for minus L to L, the Fourier series for f of x is f of x a sub 0 plus the sum n equals 1 to infinity of a sub n cosine of n pi x over L plus b sub n sine of n pi x over L, where the Fourier coefficients are calculated by first of all, a sub 0 is 1 over 2 times L, integral from minus L to L, f of x dx. And then a sub n is equal to 1 over L, integral from minus L to L, of f of x times the cosine of n pi x over L dx. And b sub n is 1 over L, integral from minus L to L, of f of x times the sine of n pi x over L dx. So this is for n greater than or equal to 1. All right. Now, what I did last time we met was I talked about a Fourier series for what? For f of x equals to x. On what interval? Minus pi less than or equal to x less than or equal to pi, right? So, in other words, L was equal to pi last time, so n pi x over L was just equal to nx. And that's why, I mean, the reason last time I did that, and I agree with, Stuart, I think, wrote this additional section for his, well-known calculus book. And I like that approach to start with because it reduces clutter in the initial discussion, right? If we focus our attention on expanding a function from minus pi to pi, then like the sine and cosine, they're not as cluttered. The pi's cancel, and you just have cosine nx and sine nx. And that's kind of the nicest the formulas can look, all right? But more generally, you have to include this L factor here like that. Because you might be interested in expanding a function around some other domain, not minus pi to pi, but maybe something else, minus 1 to 1 or something. All right? Let's look at an example. If I can. I don't know. I'm not convinced I just like working on minus pi to pi. It's so much nicer, but I will take my medicine and do this. I'm going to regret this. So f of x is pi squared x squared, right? So let's calculate the Fourier coefficients. I'll start with a sub 0. So my L, what's L equal to? Here L is equal to 1, right? A sub 0, 1 over 2, integral from minus 1 to 1 of pi squared x squared dx, right? So what's a sub 0 equal to? Pi squared x to the third divided by 6 evaluated from minus 1 to 1. Otherwise known as pi squared over 6 times 1/3 minus 1/3. So what's my a sub 0? Hey, there's no Zach today. What's that? I need to have a bonus quiz? It's just the right thing to do. I'll keep it in mind. Maybe if he doesn't get here by the end of class, we'll do something. Let's see here. Is he not here, right? I'm not wearing my glasses at the moment, but he's fine. Unless he's got some sort of active camouflage I'm not aware of. Let's see here. 2/3. What's that? 2/18. Pi squared over 9? Am I right? Confirm or deny? I'll do the b sub n. 1 over 1, otherwise known as 1, integral from minus 1 to 1 of pi squared x squared sine of what? Looks like n pi x, right? Was I wrong? Oh. Golly. Yes, thank you. It's the integral of x squared is x cubed over 3. So like this is 2 times 3. X squared integrates to x cubed over 3, right? So I should have had pi squared over what? 3, yeah. All right, there we go. Thank you. Now, how about this one? This one I can't mess up. I mean, of course, I make these mistakes for your learning, as is my custom. X squared times sine is an odd function. If you replace x with minus x, you get minus what you started with. So this is odd. An odd function integrated from minus 1 to 1 is 0. So the b sub n's are 0. This is a good contrast to my first example, where the a sub n's were 0 because we were looking at an odd function. We were expanding an odd function. This one, the function that we're working on, this is what? This is an even function, right? So it makes sense that as we're building it from a sum of sines and cosines, there aren't going to be any sines in the expansion because this is an even function, so it's going to be built from even functions, which happen to be cosines. It makes sense. A sub n, what is that then? And again, 1 over 1, which is just 1. So integral from minus 1 to 1, pi squared x squared cosine of n pi x dx. So in a different higher level math class, I would probably just skip this calculation and write down the answer. But here, this is actually a very good exercise because this is the kind of integral that you need to, like, when you see it on the final exam, just destroy it. It shouldn't take you mental effort. I mean, it's going to take you mental effort to do it. It's going to take me a mental effort to do it here in just a second. But you should know what you're going to do. What are we going to do to solve this integral? Integration by parts. How many times am I going to have to integrate by parts? 2 times, right? 1 time. Each time we're going to reduce the power of x by 1, and then we'll be done. So this is our dv1. I'll say that this is our u1, right? Actually, I'm going to say that x squared is our u1. I'm going to pull the pi squared out so that we don't have it littering the scene everywhere here. Pi squared. So if u1, if dv1 is cosine n pi x, I'm going to try to be more careful with the sign this time. See if I can do better. v1 is what? 1 over n pi sine of n pi x. I didn't miss a sign, did I? The derivative of sine is cosine, right? And I need the 1 over n pi because of the chain rule. So, great. I've got x squared. Excuse me, I've got 1 over n pi, x squared sine n pi x minus 1 over n pi integral of sine n pi x, well, let's say 2x. I mean, you can write the terms in any order you like, but the point is what I'm putting here is supposed to be what? It's supposed to be v du, right? Is that v du? Or more specifically, v1 du1? I think it is. Now, how many points would I lose at this point on my exam if I wrote it this way? The answer is about 10% on this problem, unless you fix it. Because this is a definite integral, and it must remain a definite integral, right? So that means that I haven't fully communicated yet what's going on. This gets evaluated from minus 1 to 1. This integral is also from minus 1 to 1 because we're beginning and ending with a definite integral. Right? So that's what integration parts looks like when there are bounds. You can't ignore them. There they are. Now, although that is somewhat comforting, because what happens when you plug in 1 and minus 1 here? We get sine of n pi or sine of minus n pi, otherwise known as 0. So this, 0. And what we then have is pi squared minus 1 over n pi. I'll put some big parentheses here. Now this, I'm going to call dv2. And I'm going to call the 2x u2. So if dv2 is sine n pi x dx, what's that make v2? I would say 1 over n pi cosine of n pi x if I wanted to make the same mistake I made last class. But since I don't, I'm going to do what?
What's n doing when you're integrating? Is that just like a constant?
N is a constant here. N is a fixed constant throughout this integration. More specifically, it's a fixed integer greater than or equal to 1. But as I was just saying, my v2 is not right, right? What am I missing? A minus, right? So, all right, we have minus 1 over n pi cosine of n pi x. And that, what was my u2? Oh, u2 was 2x times 2x, right? And then minus integral from minus 1 to 1, minus 1 over n pi, cosine of n pi, and 2 dx. So just to emphasize here, the integration by parts, this piece right here, right? That's going on right here. That minus 1 over n pi, I moved. Yeah. Oh, yes, definitely. What's wrong with me? Oh, so many things, but there we go. Anyway, so, and again, I have violated the prime directive in terms of, I'm going to put the 2x out here because it's less cluttered. Evaluated from minus 1 to 1, right? Because that's how integration by parts works when there's bounds. You know this. Now, so what happens? So we get minus 2 over n pi cosine n pi, right? Plus 2 over n pi cosine minus n pi. And then what's this integral work out to? One over n pi squared sine of n pi x evaluated from minus 1 to 1. So at first glance, you might think that that last integral gives you something, but it doesn't because it integrates to a sine of n pi minus a sine of pi. I mean, that's 0 again, just like the other thing was 0 earlier on in the calculation. So like this. Adios, muchacho. And, uh-oh. Yo. Oh. Uh-oh. Can you tell me where the sign error is? Why doesn't this make sense? I mean, if you take what's on the board at face value, we have 0, which would mean that the Fourier series is 0, which would be disconcerting because this is not the 0 function. Yes? Well, cosine is even, so these are equal. And so these would cancel as it stands. Yep. Distribute the minus. I suppose that's one way of looking at it, but that wouldn't help. These two cancel as they stand. There should be a minus, yes. Which one? The one after the first? Because how many minuses are there in total? There's 3, exactly. There's the minus that's here. There's the minus that comes from plugging minus 1 in. But there is a third minus, which is from FTC part 2, right? Because we're taking the lower minus the upper minus the lower, FTC 2, you know? So 3 minuses. Minus, yes. Indeed. And then I agree, distribute the, like multiply through. So we actually have what? So we get what, 4? I think. See, because I get minus 4 plus 4 cosine n pi, and I got a net of n pi squared. Let me rewrite this, yeah? So what we've got is 4 pi. Oh, the pi squareds cancel, right? So I get 4 times minus 1 to the n over n squared. Thus, x squared is, what was a sub 0? Pi squared over 3, yeah? Oh, is it x squared that we're approximating? Pi squared x squared, thank you. Pi squared x squared is x squared over 3 plus what? The sum, n equals 1 to infinity of what is it? 4 times minus 1 to the n over n squared times what? Cosine of n pi x, yeah? The reason for this squiggle, as opposed to equality, is just to own up to the reality that the Fourier series matches the function almost everywhere. But there's no guarantee that the Fourier series matches the function at like the ends of the interval. Generally speaking, the way the Fourier series behaves at the end of the interval is it will do. So like if you're finding the Fourier series of something that goes like this, like suppose this is the suppose this is the function. Sorry, I was trying to make that in the middle. If you were doing this, if this was your f of x, if f of x was given, say on, I don't know, minus 3 to 3, something like that, right? What the Fourier series will look like for that function is, it looks like f most places, right? But the Fourier series, it will take the value of the average of the function at jump points. All right? So like at this jump point, it's going to be there. It's going to be there. And then what the Fourier series does is, even though the function was originally just given on minus 3 to 3, Fourier series goes on and on and on forever. It's periodic. It's like the Fourier series is actually going to do this. And so forth and so on, forever and ever, both ways. That's what happens. So the Fourier series will give you a periodic extension of the function, which is originally built on minus L to L. That's like, if you look at the PDF that I posted for you guys, it talks a little bit more about that. But, we'll talk more about that in differential equations if you take it, probably. I just want to stop and smell the roses here for a second. This is for what? For minus 1 less than or equal to x less than or equal to 1, right? Maybe, what would happen if we plug in, let's try plugging in x equals to 1 for this, yeah? What do we get? What's cosine of n pi x? Yeah, n pi rather. So what's minus 1 to the n times cosine n pi equal to? Cosine n pi is minus 1 to the n, if you think about it. It's just 1, yeah? However you want to look at it, those sign factors cancel out, plus with plus, minus with minus. So what if we, this gives us that 2 pi squared over 3, right, is equal to 4 times the p equals 2 series, doesn't it? Divide both sides by 4, what do you got? Of course, this is pi squared over 6. And there you go. This is why the p equals 2 series converges to pi squared over 6. And this is probably how Euler knew this in 1737 or whenever it was that he learned this. Because Euler understood trigonometric series pretty deeply. Or maybe he just worked it out because he's Euler, I don't know. But I wasn't there. But I find this to be a somewhat comforting reason. Although, if you take a hard look at the argument I just gave you up in the corner, you should be a little bit bothered by this because I've just applied, I put x equal to 1, which is right where it's on the edge, isn't it? And, Oh, I guess that's okay though, because for this function, what would the picture be? The original function is pi equals x squared, right? So that's the original function. What's the extension? The extension would be this, right? This is what the Fourier series looks like. So yeah, it's okay. It makes sense that we can evaluate at the end and the series converges. So you see, if I did this one at the end point, it would have jumped. You know, it wouldn't have made sense to plug in x equals to 1 into the function we were approximating for such an example as this. For f of x equals x squared, it's continuous at the gluing point. So yeah. But anyway, there you go. P equals 2 series. That's how you can derive it. That's pretty much all I have to say about Fourier series. I mean, there's other interesting things in the thing I posted about, you know, the decomposition of music and so forth. I'll let you read that. Yep.
How do you know if convergence like oscillates? Like, if you just did it at one point, or you just did it at n equals 1, so how do you know that it converges to pi squared over 6? Plus, like, in like the graph, it doesn't converge anything.
Well, this is, you know, at 1, and this would be minus 1. So if I plug in 1, I'm saying that, you know, there's no jump point there, so the Fourier series should converge to the function it's modeling. It's at points of discontinuity that the Fourier series will converge to like the midpoint of the jump. That's a theorem I haven't proved. There's other much uglier things, like if you take a Fourier series, you can take a Fourier series which converges, something like, I think this one converges. Like, consider this. There's a convergent Fourier series. What happens if you differentiate it term by term? What happens if we assume term by term differentiation works? What do you get? If there's any justice, we should be able to differentiate term by term, right? Which would be what? N cosine nx, yeah? Which gives you that, which is, by the way, divergent. Because there's, you know, the 1 over n makes that converge because it gets small. There's no 1 over n here. So what I'm telling you is what I haven't told you about Fourier series is vast. The convergence and divergence theory for Fourier series is much more complicated than power series. I'm just showing you the first step. I really have not told you enough to understand convergence or divergence. The theorems of convergence and divergence in term-by-term manipulation for Fourier series are more complicated. Yep. Uh-huh.
Would you say that for even functions, that you can use it at the endpoints for odd ones?
I think that's fair. For even functions, we can use it at the endpoints. For odds, we can't. That seems right to me at the current level of discussion. But if you had an odd function which happened to go back to 0 at the gluing points, it would still probably be okay. But more generally, if your function has some sort of discontinuity in the interior of its domain, that can also be a problem. That's what this symbol is for. It means it's mostly true, but there's some finite set of points where it's a lie. So it's true almost everywhere. That term, almost everywhere, you might think I'm just being sloppy. That actually has a technical meaning, which is only clarified later in the study of something called measure theory. But anyway, listen, I also promised you guys another example of polar stuff. So, by the way, this is the end of the Fourier stuff. So unless you guys want to ask me another question in a future day. I mean, there's also your quiz. I'm giving you a quiz on Fourier and polar. Mostly polar, a little bit Fourier. It probably should be Monday, right? Yeah. Unless you guys want to come in Saturday. What's that? You come in Saturday? My goodness. You guys are funny. Make it a take-home quiz. Interesting. You would love a take-home quiz? All right, I will consider it. Let me meditate on these things. I'll make an announcement later. Listen, so I wanted to show you an example which involves a certain subtlety in calculating areas of polar coordinates that hasn't come up in previous examples I've covered in here. So it's important to talk about it. I think this is probably the simplest example that I could come up with where it happens. Something like r equals to, say, theta plus 1. All right, so r equals to theta plus 1. It starts out at 1, right? And then what happens as it goes around? It spirals out, right? When it gets back to, this is at theta equal to 0. When it gets back to 2 pi, we're at 2 pi plus 1, which is what? Like out here somewhere, right? So I probably made that, let me make this a little bit smaller so we can actually get it on here. So what I'm saying is, looks something like that, right? And then it continues to spiral out. Whatever, okay? Now I could ask a question, right? Find the area bounded by the spiral and a couple of rays. Right? Suppose I want to calculate, I want to find the area bounded by the spiral between the, the first, basically, I want to find the area, let's say, in here. What if I wanted to find that area? How would we do that? So between the first and the second place the spiral hits the first quadrant, right? So what's the inner radius, what's the outer radius? Because that's what we have to do, right? The formula for area, as we've discussed, the integral, right? 1/2 r out squared minus r in squared d theta, right? Over the range of theta that describes the region. Now, theta 1 and theta 2, maybe they're easy enough to figure out what they are. What are they? It looks to me like theta 1 equals to 0 and theta 2 equal to pi over 2, right? And I can take the half out front, fine. Right? So what's r out? Well, what's r out? It's theta plus 1, right? What's r in? It's theta plus 1, right? So, oh man, despite the appearance, it looks like this area is 0. What's up with that? Is this area 0? Yes. No, it is not 0. Yep. It is undefined. It hasn't been clearly, well, I think it's pretty well defined on the board. I mean, I know, I mean, I can kind of shade it in, right? It looks like it's finite, it's bounded, you know. I think there's pretty good hope for it being well defined, but what is it? Yep. 2 pi theta plus 1. I think she's on the right track. Let us play a much more specific game. Let me pick a point. Let me pick the initial point. This point right here, right? What's the coordinates of that in polar? Polar coordinates. It's Rn equals to 1 plus theta, right? Or theta plus 1. And theta equals to theta, right? I mean, whatever you want to call it. We could call it theta naught to emphasize I'm thinking about a fixed point if you like, all right? All right. What about the outer, what about this point? This is at Rn equals to what? I mean, R out is what? It's theta naught plus what? See, it's not theta naught anymore that you're at. You're at theta naught plus 2 pi plus 1. So the point is, it comes from this, I warned you about this at the start, the geometric degeneracy that every ray through the origin corresponds to multiple angles that will sometimes rear its ugly head in actual calculations. This is an example. Because there's a different, we can't use the same theta for both in the sense. So in short, I shouldn't do this. I should do theta plus 2 pi plus 1 squared minus theta plus 1 squared. And by the way, I need to use it like, I need to do it like that because I've already said the bounds going from 0 to pi over 2, right? You can see that theta naught should be between 0 and pi over 2 for the initial spiral, right? And so with that adjustment, this won't be 0, and we can calculate it pretty easily. A lot of things should cancel out here. Yeah, fine. I probably shouldn't hurry because I'll just write it down wrong. I've only got like a minute left, so I'm just going to stop here. But you can finish this integration, right? It's not like a big deal. Once the main thing here is understanding that we have to adjust the formula for the radial function so that they're both based on the same theta. So, like I said, we have to think about polar curves parametrically from the outset. So, I know this is subtle, but this is, it's part of the game. So, anyway. Good week of classes, right? Sorry. Yeah, I had to give a talk in Arkansas. I had some of my previous students have gone to grad school there, and they invited me to give a talk, so that's where I was. Exciting stuff, but it was good. I got to harass some students that I haven't for a while. I feel like I did my job. Oh, top hat, right? If it's 1999. So I have put in your participation grade, by the way, in the Blackboard, so it's in there. It's 75 points, like required. The rest I said quizzes and participation was, what was it? Yeah, 125, I think it was, or 120, I forget. And so I made 75% of that, 75 points of that participation. All of you who are here have at least that. Most of you have 80 or 85. So you will not lose points on your participation. And I still haven't added the bonus for, healthy top hat percentage. I think there's only one person here who's not going to get that. Sorry. But, I can't comment on specific persons. I can't comment on specific persons, but no, it's not Zach. Anyway, 93.75. Party like it's 93.75. There you go.